طيب بسم الله الرحمن الرحيم. We talked about the basic definitions for security mechanisms and services and the different types of attacks. So some basic fundamentals about network security. Here also it's still part of the applied cryptography course that we talk about symmetric encryption and message confidentiality. So in this part we talk about symmetric encryption. طبعا we have a plain text that we pass through an encryption algorithm. In here you studied before DES with triple DES or AES with difference between them. And then this, and here we have what we call ciphertext. This ciphertext gets communicated through the network channel. Okay? In which case the assumption is that the attacker here, okay, we have to assume that the attacker knows exactly what the ciphertext looks like. So the attacker has clear idea about the ciphertext. All the ciphertexts that are being communicated, it's visible to the attacker. You have to have this assumption. Okay? Then on the other side, we have the decryption algorithm or the decipher, okay, to reverse the ciphertext into what we call the plain text, which is the one here. Of course, symmetric encryption talks about the fact that in order for the encryption algorithm to work, encryption and decryption, they have to share the same key. Okay? So there is an assumption that there is a stage before this network model, okay, in which this key is shared to both the transmitter and the receiver. How about it's not our problem, but the key has to be shared. Sometimes it's through a shared server or whatever means. في key exchange techniques أصلاً, which is outside of this, okay? But the end result is that the key is one key and it's shared to both. Why do we say this? Because as part of the key exchange, we might have attacks أصلاً as part of the key exchange, okay? But this is not our problem. Our problem is that we assume that the key is secret and the only two entities that know that key is the transmitter and the receiver, in which case we can use one of the encryption techniques, DES, triple DES, whatever, add the transmitter to encrypt, convert plain text to ciphertext, and then here we convert ciphertext back to plain text, as long as we use the same key. So this is what we call a type. What are the requirements of this symmetric encryption? The requirements is not that the encryption technique itself is secret. No. Okay? The symmetric encryption technique itself is public, is known, but it needs to be strong. Okay? يعني strong. This is a fluffy word. يعني كلمة strong. Strong معناها إن if you have the ciphertext, which we assume that the attacker has access to that, right? If we have the ciphertext, it would be computationally infeasible, okay, to get back to the plain text. Okay? Given that the encryption technique itself or the encryption algorithm is known. Okay? So we achieve this by having a secret component, which is the key. So the only secret component here is the key, not the algorithm. The algorithm itself is known, it's public. Okay? But the algorithm needs to be strong to make it computationally infeasible for anyone, if you have access to the ciphertext, to get back the plain text. Why do we say it's not impossible? Because it's really not impossible. It's always possible. Okay? So the term computationally infeasible is an accurate term. Because it's always possible. Okay? So theoretically, if you give me a ciphertext by making certain assumption on the plain text. As we said before, we can assume that the plain text مثلا is English, is كذا. So we can use exhaustive techniques, exhaustive search, okay, on all combinations of the key, okay, and get back the plain text. طب ما هو, this means that everyone will do this. No, why? Because if they do this, they will spend huge amount of resources, more than the value of the information they are trying to break. But for them, it's not feasible. Okay? This is the job of the encryption algorithm. ماشي؟ واضحة النقطة دي؟ Sender and receiver must have obtained copies of the key, and as we said, how? We don't say how here, because it's not our problem. There is a key exchange technique, okay, which we will talk about later. So the security of the symmetric encryption depends on the secrecy of the key, not the secrecy of the algorithm. The algorithm itself is completely public. And not only that, sometimes, one of the requirements, which is not listed here, of the encryption technique is that it's strong, but it can be modeled easily. بمعنى, I will show you now the physical structure and how easy it is that you can make it, you can model it easily. And this modeling, okay, makes it really spread very fast, okay, and allows many vendors to implement this encryption algorithm on different forms, whether it's software or on chips or something like this. Okay, we'll talk about this further. So manufacturers, they can and have developed low-cost chips implementations of this data algorithm. And in order for them to do this, the algorithm has to be known, has to be public, okay, and it can be realized easily. Just the fact that it's strong, it doesn't mean that it cannot be developed easily. So it needs to be strong from the security point of view, but it needs to be easy from the development point of view. And these are conflicting objectives. But that's why the requirements is not easy. طيب, what are the main, they call it dimensions, or the main categorization of these cryptography techniques? So cryptography or encipherment techniques. So it's the first dimension, or the first factor we need to talk about, the type of operations used for transforming plain text to ciphertext. Okay? What are the common types of operations that it can be done by the cryptographic technique in order to convert the plain text to ciphertext? One thing is substitution. And what that means is simply is that we have a big plain text. This is the plain text. Okay? So we take small parts of the plain text, let's say like 1 character, 2 characters, 3 characters, whatever. Okay? We take this, and then based on the key, we can use the key to do some lookup in a lookup table. This lookup table could be easily the alphabet ABC. Could be مثلا اللي هو ASCII codes. ماشي? Could be anything. Okay? And based on these characters, we look at the key. The key will give us like the index of where we take the combination in the lookup table to perform the ciphertext. So each of these parts will be substituted with another part based on this lookup table. Corresponding part based on the lookup table, and we look up the table based on the key. The key can give us like the index in the lookup table Okay? A very famous example is the Caesar cipher. I'm not sure if you are familiar with Caesar cipher. Caesar cipher يعني basically يعني it assumes that you have مثلا إيه? You have the messages A, B, D, whatever. We take each character and we say what is the index of A in the alphabet is the first character. But the key is 3. Okay? So we take the E, we add to it 3, it becomes D. صح? So we substitute A with D. That's it. Very simple. Okay? So this is what we call Caesar cipher. So based on the key, we look at the alphabet, we convert, we substitute the letter with another letter based on the alphabet. Very, very simple. This is what we call a substitution. ماشي? Transposition talks about the fact that we don't substitute. No. What we do is that we take the plain text, we divide it into smaller parts, yes, but then we shuffle these parts based on the key. Okay? So we don't have an external lookup table. We don't have substitution. We have a permutation of the same. So the content will still be the same. It's just that it's rearranged. Okay? So it's not a substitution. It's we call it transposition or rearrangement. ماشي? So the general format of cryptographic technique is actually a combination of these two operations. ماشي? So you have substitution and rearrangement. Okay? And you have these substitution and rearrangement in a complex form. You have to do many substitution and rearrangement in a complex form. واضح كده? Which is what we call the product system. So the product systems is nothing but it's a combination of substitution and transposition, okay, in certain form. ماشي؟ واضح كده؟ تمام. طبعا another dimension is the number of keys. If the number of keys is 1, this means that we're talking about symmetric encryption, which means that we have one key at both the transmitter and the receiver. And there is an issue with this. How can we share this same key into two different systems? While we are sharing this, there might be some attacks, leak of information, things like that, issues that we don't have to go through now. But there is another form called asymmetric encryption. Asymmetric encryption is or sometimes they call it public encryption. It talks about two keys. There's public key and private key. ماشي? So we'll talk about this public key encryption later on. Or the way in which the plain text is processed. This is very important. So there is block cipher and there is a stream cipher. Okay? This is very important. Block cipher here talks about the fact that so block cipher talks about the fact that you have a big plain text like this. Okay? Let's say like a video file or something. So what you do is that you divide this into block 0, block 1, and so on until block n. Okay? Each one of these blocks, independently or in a certain type of pipelining, but let's say independently, we will apply encryption algorithm of some sort, AES, DES, whatever. We produce cipher block 0. Okay? And then here, we apply the encryption algorithm again, the same one. Here we can use the same key or different key. Okay? So we can use the same key for all of them, or we can use different key. But if we decide to switch the key, okay, then we have to switch the key at the receiver as well. Then we, again, block 0, block 1 will be cipher block 1, and so on. Okay? Then we transfer these blocks over the channel. So we have the channel. This is the This is the wireless or wired channel or whatever. ماشي? Then we get here cipher block 0, cipher block 1, and so on. Then we have to do the reverse operation at the receiver, again assuming one key or different keys. So this is key 0, this is key مثلا 0, this is key 1, whatever. But you have to synchronize. If you use key 0 here, you have to use key 0 here. If you use key 1, you have to use key 1. If you decide to change the key along the way, you have to make sure that it's identical at both the transmitter and the receiver. Okay, and from this we have to apply the decryption طبعا, and then we get the original blocks. ماشي؟ طيب. So this is straightforward. What is the problem here? The problem here is that if for whatever reason these blocks have changed by the channel, okay, for any reason, whether due to attack, like for example some integrity attack or some active attack tries to manipulate, or network error. If you use مثلا UDP, we all know UDP is unreliable, صح? So UDP is unreliable, so you have some error in the network. Okay? So if you have any one single bit in the cipher block, okay, the problem is that you can never actually achieve here the same block 0. Okay? So for example, مثلا take an image, divide it into blocks, and then introduce any kind of network error to it. You will not be able to see anything in the image on the other side. خلاص, it's done. Okay? Why? Because of this. Because as part of encryption, I had to do lots of rearrangement and substitution and transposition and so on, right? So if one small bit in the block is in error, I cannot recover the whole block. The whole block is damaged. خلاص. ماشي؟ واضحة دي؟ طيب, why am I saying this? Because the stream cipher tried to solve this particular problem. So if we try to use the stream cipher changes that concept slightly. We have the plain text. This is the plain, it's big, okay? So what we try to, of course, here we have keys, we have the encryption algorithms and so on. The طبعا examples of the block ciphers is a DES, triple DES, AES. All of these are block ciphers with all the operational modes. I'm not sure if you studied the operational modes, the counter mode, the cipher block chaining, and so on. All of these are block ciphers. ماشي? The stream cipher works differently. We will deal with the plain text as a stream of bits. For us, it's a stream of bits. We don't divide it into blocks. ماشي كده? It's a stream of bits. So based on the key, okay, we will try to generate another stream of random bits. Okay, based on the key, we will generate as many bits as we want, based on the key, using what we call random generators. Okay? And then the stream cipher becomes very easy. We take these two and we XOR them, and this will be the ciphertext. Okay? So that's a different concept now. So block cipher divides into blocks. Stream ciphers doesn't do this. It actually generates a random stream in parallel to the plain stream, and then all we need to do is just XOR, XOR, XOR. Okay? Type, what is the property of this stream cipher compared to the block cipher? If you have the cipher text now will again be transferred over the channel. Okay? If you have any error due to the channel, okay, the error will in fact be a localized. The effect of the error will be localized in a, يعني مثلا if you take an image or a video file and then you use stream cipher, ماشي? Along the channel you have changed some bits. You will see that the image is still the same, maybe 1 bit or 2 bits have changed. ماشي? But you will be able to recover the image if there is any manipulation or if there is any error that happened in the stream cipher operation. So the stream cipher has the property of preserving the content of the information even under channel error. ماشي? Block cipher does not have this. Okay? But as we will discuss in a minute, stream cipher has a security problem. Okay? As we can see here, it's just that you generate a parallel stream and then you XOR. Okay? You make the life of the attacker easier in that case. Why? Because of what we were going to discuss in the next slide. ماشي? So stream cipher is not strong from a security perspective, but it's error tolerant, okay, from the network perspective. Block cipher is very strong from a security perspective. It makes the job of the attacker much, much harder. Okay? But it's not error tolerant. اتفضل. That's another big advantage. Okay? The stream cipher is much faster. Okay? Is much faster. Because here in the block cipher you have to do lots of permutations and transposition and stuff like this, right? Here you still need to do some of this, but within the random generator. Here there is what they call random generator. Okay? So this random generator, based on the key, it generates a stream. Also based on some operation, but usually this operation, the complexity بتاعتها much less compared to the complexity of the encryption algorithm. So the ciphertext is much less complex, and it's more error tolerant to the network errors. But that doesn't mean that it's good in all aspects, right? Because it's weak from a security perspective. You can break this easily. And I will tell you why now. So this Vernam Cipher is actually what we used for the stream cipher. The Vernam Cipher here is one of the simplest ciphers, based on which you say, I will have the key stream generator, okay? And I will XOR this with the plain text, and this will be the ciphertext. Okay? So basically, the ciphertext is in fact the plain text XOR'd with the key. Okay? So if you have multiple plain text مثلا files or something, okay, then you have ciphertext 0 equals plain text 0 XOR'd with the key. Ciphertext 1 equals plain text 1 XOR'd with the key, and so on. And again, this is a symmetric encryption, which means that the key is the same. ماشي? Then if you want to, at the decryption side, what is the plain text? It's in fact the ciphertext XOR'd with the key. That's it. Okay? So again, here, this Vernam cipher is very simple, صح? There is some mathematical proof, by the way, that despite the simplicity of this, is that it's very much protective against the attack if you don't know the plain text at all. Okay? So if the only thing they have access to is the cipher text, you cannot really break down this XOR combination. Okay? But this is a naive assumption that the attacker has access only to one ciphertext. The attacker may have access to one plain text. Okay? If the attacker has access to one plain text, bas, okay? One plain text. So the key becomes the ciphertext I XORed with plain text I. That's it. So if you have access to one plain text, you can break the key. One plain text بس. Okay? هتقول لي طب يعني هو how can I have access to one plain text؟ أقول لك okay. In a network protocol, sometimes مثلا let's say HTTP protocol, sometimes you have to send a specific format of the HTTP header as part of the connection establishment. Okay? So some attacker might say, okay, so I'm expecting that you are trying to connect to a web server, so most probably the HTTP header will look like this. Okay? So based on this assumption, I can read the ciphertext and XOR it and get big part of the key. At least big part. Okay? So if I get big part of the key, I can use exhaustive search to get the missing parts, and I can break the communication easily in no time. That's why the Vernam cipher usually is not very strong from a security perspective. Okay? But it's very simple, very fast, and it's used in stream ciphers a lot because it's also error tolerant from the network point of view. So again, if you have access only to all the ciphertext, okay, the only way you can guess the key is by exhaustive search, which is what we want to have, right? But this is a naive assumption because the attacker can always assume that you are communicating. يعني مثلا at the beginning of the communication, most probably what are going to say? Assalamu alaikum. خلاص, okay, so Assalamu alaikum is a plain text that I'm expecting at the beginning of the communication. Okay, so I will assume that one plain text will be Assalamu alaikum. Okay, so I know the ciphertext that corresponds to this. Once I have one ciphertext and plain text, خلاص, and I got the key. Here, I only need one combination only. Okay, but for AES triple des, if you have plenty of these, you will never be able to guess the key. You will not be able to get this, and I will show you now.
Doctor, if you do the same process, but instead of storing it, you put it into a hash map, wouldn't it be a lot more secure? And
hash map?
Yeah, like if you hash it.
لا, it's a different technique now. Hashing is totally different. This is encryption. The fundamental difference between encryption techniques and hashing techniques is that hashing is one-way operation. It's not for reverse at all. Once you hash something, you can never reverse it back. This is a fundamental difference. Hashing is used in different contexts. We'll talk about this. Here, encryption requires decryption. So I have to use encryption in a way that's reversible. It has to be reversible. This is one of the requirements. ماشي كده؟ Hashing, بالعكس, one of its requirements, it's not reversible.
One-way function.
It's a one-way function. Okay? ماشي كده؟ So here, this is the Vernam cipher. Good from a network perspective, fast, and so on, but it's not good from a security perspective. تفضل.
The key should be as long as the length.
Of course, here with XOR, yeah, that's why yes, for Vernam Cipher, you assume that the key, because it has to be XOR, so they have to be the same length, right? But of course, the stream cipher does that in a stream fashion. بمعنى إن أنا I take few generated bits, I XOR it with the plain text to and this, but overall, I have to have as many generated bits as long as the stream بالضبط. يعني they have to be يعني the same length بالضبط, the same number of bits. ماشي؟ but هو ايه اللي بيحصل بقى في الستريم سايفر؟ I read the plain text in small مثلا 3 bits 4 bits okay وبعدين I XOR them with the generated bits and then I take the next 3 generate and XOR generate and XOR generate and XOR and so on ماشي but I don't do بقى ايه ولا substitution ولا transposition ولا الكلام I don't do any of this هو كله XOR وخلاص. When do I do بقى transposition in the random generator. Random generator generates some random stream of bits based on the key. And that's what's done in A. What is a technique that uses stream cipher?
What's the question?
Hmm?
What's the question again?
What is the technique that can be categorized as a stream cipher? One-time pad is not an encryption algorithm. It's a protocol.
Something like A5.
A5 اسمه RC4. RC4 is an example of stream cipher. We'll look at it now. طيب crypto analysis زي ما قلنا احنا just the fact that the encryption algorithm is strong, it doesn't mean that it's unbreakable. Everything on earth is breakable. It is breakable. It's just how much time we spend to break it. Okay? So an encryption is computationally secure. ليه بنقول computationally secure؟ يعني معناها if you want to break it, you have to spend some amount of computation that makes this process infeasible to you, uneconomical. يعني what are you going to gain ماشي مثلا to break let's say حتى a bank account ماشي of someone who has 10 ريال in the bank مثلا ولا 1000 ريال in the bank, and in order to guess his password ولا to break his account you have to have a server ماشي to do exhaustive search, and then you break and know his password, and then when you log on to his account you find that he has like 1000 ريال. You spent huge machine to break his account, and at the end what he has in the bank is not really worth what you have done, right? If you know that he's a billionaire, that's another story. But يعني sometimes you spend huge amount of resources and money and computational resources to break information which is not really worth that much. So that's what we talk about here. It's not that it's impossible to break, it's always possible. ماشي؟ يبقى the cost of breaking the cipher exceeds the value of the encrypted information. That's what we want to reach. ماشي؟ And the time required to break the cipher exceeds the useful time. ليه بقى؟ إن sometimes ماشي إحنا during the communication we know that there's nothing unbreakable صح؟ بس we know that مثلا in order for anyone to break the communication you need to spend on average 3 hours. Okay? طيب خلاص احنا we'll change the key every 2 hours. Okay? So every 2 hours we use different keys. خلاص. Then you spend forever. You spend all your life trying to break it. ماشي كده؟ So we make the lifetime of the key less than the practical lifetime of anyone to break the communication. ماشي؟ طيب this is what makes anything breakable is it all comes down to brute force. Brute force معناها ايه؟ we try all different combinations on Earth. Okay? So we have access to all the ciphertext, right? So we get the ciphertext, we get even one ciphertext, and we try all possible combinations until we get, but we have to make certain assumptions on the plain text. The plain text مثلا is plain English, or the plain text مثلا has a header of certain format. ماشي? So we know that the encryption technique itself is public. We know what it is, right? We know that it's DES or triple DES or AS. So we have the encryption technique. Okay, what we don't know, the key. صح? So we try different combinations on the key, and then we apply decryption. We do that millions of times. Okay? So the theory is that if يعني مثلا if you have a key of length مثلا n, okay, this key is binary. It all comes down to binary. It all goes down to binary. ماشي? So if you have a key of length n, what is the number of combinations for any binary combination of length n? 2 to the power n. صح؟ Okay. صح ولا مش صح؟ يا ناس بتوع النتورك 1 صح؟ Okay. So if you have a key of length n, you need 2 to the power n different combinations, okay, to try all the combinations. ماشي? So if we try 2 to the power n different combinations, one of them هتظبط يعني one of them will break the communication. And this is what we call brute force. ماشي? So يقول لك on average طبعا احنا if we try all the 2 to the power n, we don't have to يعني مثلا واحد جه مثلا after 2 to the power مثلا 3 طلع حظه حلو, and then we found okay, so the plain text looks familiar, so this must be the key. مش متخيل I don't have that to do more يعني مش حافظ انا يعني خلاص I will stop here, right? I broke the communication. خلاص I stop, right? So this can happen in the middle. صح? This can happen later, can happen. فبيقول لك on average statistically يعني the number of combinations you need to do is in fact 2 to the power n minus 1, which is half the 2 to the power n. معروفة 2 to the power n minus 1 is half, right? صح? Okay? So statistically, on average, if you know that the key is of length n, okay, on average, you need to do 2 to the power n minus 1 different combinations to break the communication. Okay? So that's why we say that the larger the key, the better, right? But also the larger the key, the more complex, okay, the encryption algorithm will be. طبعا. Okay? فthat's clear. To supplement the brute force approach بقى, some people they try to use intelligence. ما احنا بقى يعني we don't have to blindly يعني try all different combinations. We can always use our intelligence to reduce يعني the complexity. That's what the attackers do. Do not think that the attackers they always use brute force. Okay? That's why we have hackers, right? And we have normal people. The hackers, they use intelligence to try to reduce these combinations. Okay? So instead of spending مثلا 100 hours to break the communication, they spend a few minutes. ماشي? So they have to use intelligence. They use by intelligence in different ways. Sometimes they use intelligence يقول لك طبعا خلاص يعني I don't have to I can try to do man-in-the-middle attack to try to leak مثلا more ciphertext, and then I try to make assumptions on the plain text, okay? Or I can try to fool the sender. أقول له take this plain text as if I'm the receiver. Take this plain text and give me the ciphertext, something like this. So I give him the plain text, and I get from him the ciphertext. Okay? So I'm controlling the plain text that I give him. So I can give him something simple, so I can get the ciphertext and try to analyze by different combinations of plain text and ciphertext, plain text, and this will allow me to reduce the number of combinations. So this is what we call a cryptanalysis. This is what we call cryptanalysis, and this is what many of the hackers or many of the attackers do. So they have to use some degree of knowledge about the expected plain text. ماشي? Whether it's in plain English, whether I know that at the beginning of the communication we have a network header of some sort, so I know what the plain text looks like, things like that. Okay. طبعا one of the things that it has been used يعني in the beginning of standardizing the encryption techniques is what we call FEISTEL structure. Did you study this in applied cryptography? You must have. You have to. So the FEISTEL structure is a structure that was actually standardized or defined by NIST. Okay, it's not an encryption technique per se. It's actually a structure that has been studied to achieve the requirements for security. Later on, they have used the FEISTEL structure as part of the DES and triple DES. But FEISTEL structure itself is not an encryption technique. So what they said is that in the FEISTEL structure, we have 16 different rounds. So we have 16 rounds. So we have a plain text, and because this is a block cipher, okay, so we have a block of fixed size. So this is 64 bits. This 64 bits, we'll divide them into two parts, left element and right element. So each part is 32 bits. Okay? So we take the left element, okay, and we XOR it with the right element after applying a function, a certain function. Okay? This function, by the way, can change. Okay, but it has to have a certain requirement. So again, this function itself, inside it, there is substitution and transposition inside it. Okay? And then we XOR it to reach to the right element 1 in round 1. Okay? And then the right element goes to the left element, and by doing this, we achieve round 1. We do this repeatedly 16 times. Okay? And then what we will achieve at the end is a ciphertext that will achieve the requirements that we talked about. So this is a strong encryption algorithm. It uses transposition and substitution in a combinations that's not easily breakable. Okay? And even if you have ciphertext and plain text, many combinations, you will not be able to break this easily and get the key. And the more rounds you have, the stronger the encryption algorithm will be. And that's why NIST they have used some analysis. Sometimes you have to analyze this from an information theory perspective. They have analyzed this using some math. That's why this is an intellectual property. It's not كده it's not something out of the blue. لا they have analyzed this from information theory perspective. Okay? And شوف بقى the beauty of this is that if you model this using certain equations, you find that really the right element of round I, okay, in fact equals to what? Equals to the left element of round I minus 1, صح اللي هو ده؟ صح؟ XOR with the function, okay, which is a function of key I, okay, and right element of I minus 1. Okay? Then the left element of I, simply A, is the right element of I minus 1. Okay? So we have done these two equations recursively 16 times. طيب ليه انت بتعمل كده؟ And I want to prove to you that by converting this complicated encryption algorithm into mathematical equations, the strength and the analysis of this encryption algorithm is perfectly possible and feasible using these equations. I can study these equations from information theory perspective, okay? And also it simplifies the development of this algorithm, okay, by the manufacturers and vendors. Okay? So by modeling this complex encryption algorithm into some mathematical equations, it helps us to achieve these two things. We can really analyze the strength of this encryption algorithm from information theory perspective, which طبعا obviously we will not do because it's very mathematically intensive. And also manufacturers can use this to develop these encryption algorithm easily in different formats. But software, I can program this on Python very easily, صح? It's a recursive function, صح? Recursive function, I can develop it on Python very easily. I can develop it on a chip, hardware, Raspberry Pi, whatever. I can use it in different formats, right? And it's proven to be strong from a security perspective. ماشي? Of course, the reverse operation of this is the decryption. Okay? FEISTEL, they have come up with this, and they said that this FEISTEL structure, it achieves these requirements, and it has this analytical benefits. ماشي؟ We were able to analyze the encryption algorithm on different factors. We were able to take this and use it as a building block for the DES, ماشي? To build the first standard encryption technique, which is a DES, and later on triple DES and so on. طيب. So what is the خلينا okay خلاص we'll stop here عشان أنا مش overtime زي المرة اللي فاتت.